The conditional expectation is the sum of the products of the payoffs and the conditional probabilities. However, if the probabilities are determined using a joint distribution, the conditional expectation is the sum of the products of the payoffs and the conditional probabilities. For example, let X and Y be the number of claims submitted in 2 consecutive months and assume our joint probability distribution looks like. Let's find the expected number of claims in the second month given that exactly 2 claims were submitted in the first month. So we need to find the probability that we have some number of claims in the second month given that X equals 2. So we need to find the probability X equals 2. So if X is 2, then for any Y greater than 0, we have the probability that X is 2 and Y is whatever it is will be. And note that the probability that X is 2 and Y is 0 is just 0. So while we should compute our sum over all possible Y values, we can start our sum at Y equals 1. Now, taking a look at this sum, we have a constant factor we can remove. And note that this is a geometric series, and the first term of that series is going to be when Y equals 1, that's going to be raised to 0 power to the 1. And so our geometric series summation formula tells us that this series will have a sum of, which we can simplify, and we get our probability that X is equal to 2. Now our conditional expectation, that's the expected value of Y, given that X is equal to 2, well, that's the sum of the products of the payoffs and the probabilities. Now that conditional probability is going to be, so this is just the probability given by our joint distribution function. The probability that X equals 2, that's 3/16. And so this simplifies to now we can find the sum in 2 ways. Notice that the summands are suggestive of the derivative of a kth power. And so that suggests we can obtain it by differentiating a power series. Now remember, 1 minus e to the negative 2 is some value, so let's let x be equal to 1 minus e to the power negative 2. And so our series becomes, and again we can view this as the derivative of a power series, and e to the negative 2 is a constant, so we'll remove that factor. And this power series we should recognize as the power series for 1 over 1 minus x. And we know how to differentiate that. And our sum will be the value when x equals 1 minus e to the negative 2. And that will be alternatively, note that the probabilities have the form something times a power of 1 minus something. So this is the expected value of a geometric distribution with that probability, which will be the second. Now it's important to realize the best way to solve the problem is both ways. You should be able to recognize the probability distribution, but being able to find the sum of a power series is also very important. Or let's consider another problem. A driver and a passenger are in a car accident, and each has independently a probability of being hospitalized. And if a hospitalization occurs, we have a uniform distribution of the loss amount. Assume independence, and let's calculate the expected number of people in the car given that the total loss is less than 1. So here what we're looking for is actually not part of the random variables we're given. So let z be the number of persons hospitalized and x and y be the total loss. We're going to find the expected value of z given that the sum is less than or equal to 1. Now let's think about this. If we let x and y represent the losses from hospitalization, the event that the total losses are less than 1 corresponds to the region where their sum is less than or equal to 1, and we need that probability. So there's 4 outcomes where we land in this region. First of all, if neither are hospitalized, then our sum is 0, and so that's going to occur with probability. If the driver is hospitalized but not the passenger, then because the loss amount can't exceed 1 for any individual, then we're guaranteed that the loss is less than or equal to 1. So that has probability. And likewise, if the passenger is hospitalized but not the driver. And the only case that we do have to do a little bit of work for is that if both are hospitalized, but the total loss is less than 1. So the probability that both are hospitalized is 0.3 times 0.3. And since the probability is uniform within the region, the probability the total loss is less than 1 is 0.5. So the probability both are hospitalized and the total loss is less than 1 will be, and so the probability the total loss is less than 1 is the sum of these 4 probabilities. So again, z is the number of persons hospitalized, and so we want to find the conditional expectation of z given that x plus y is less than or equal to 1. So either 1 or 2 people are hospitalized, multiplied by the conditional probabilities. And so those conditional probabilities will be